Morning, everyone. So far in this chapter, we've looked at three different theories of acids and bases. We started off with the Arrhenius theory. This is the one that when you drop this chemical into water, it ends up releasing off protons, the characteristic H plus for an acid. Base's job here will similarly release off a hydroxide. That's the typical base molecule. As we work towards a more broad Bronsted-Lowry definition, we're going to spend a lot of this chapter focusing on those conjugate pairs. We started looking at a Bronsted-Lowry acid as a proton donor. It ends up releasing off an H+, whereas a Bronsted-Lowry base is just a proton acceptor. Usually, if the chemical receives the football and holds on to the H+, it ends up leaving behind the hydroxide that we expect for a basic solution. Yesterday, we ended off looking at a Lewis definition as well. This one here had to do with the ligand chemistry that we did last year. And basically, as a Lewis base, it not only donates electrons, it donates an electron pair to end up coordinate bonding. The Lewis base is the electron pair donor, while the acid is the electron pair acceptor. So I'm just going to finish off that question from last day here. We had an example where we wanted to see the reaction between water reacts with sulfur trioxide in forming sulfuric acid. Since it's called the Lewis definition here, we may as well start off with the Lewis structures for these ones. So starting off here with water. Although water overall is a neutral molecule, it does have these two electron pairs right here. Our sulfur trioxide here, by the time you run out of electrons, we end up having this picture here. Usually when we run out of electrons, what we would do is we would then make a double bond. Well, remember, it could be, this one making a double bond, or it could be the other one here. This one here already shows resonance. That would actually add stability to this. In this reaction, what's going to happen here is the water is going to take its electron pair and actually attack the more electropositive part of the sulfur. As that happens, the one that's equivalent to the double bond actually just jumps back up like that. So we're going to end up having, let me see if I can keep it color-coded for you. So we have water. We just made a new bond here to the sulfur. The sulfur currently has just three, what looks like single bonded oxygens here. Basically, it's being attached. Subsequently, what's happening in this case, eventually we will actually want to pick up another hydrogen. Where that other hydrogen comes from as sort of a ladder step. The ladder step is going to be the electrons from the water actually is going to go back down to the oxygen, and it's going to actually release off this H as a H+. Seeing as there's an H+, this HSO3 chemical can actually bond with that H+, and therefore forming two H's and SO4. Yes, we know sulfur is an expanded octet, so typically what's going to happen, if I just clean that up a little bit, we're going to have the equivalent of two double bonds, and overall we're neutral because of the proton canceling that charge there. Right? So that's a way that we end up seeing the Lewis acid Lewis base here. The first attack was because of this water. So this one here is referred to as the Lewis base, and the SO3 sulfur trioxide is actually known as the Lewis acid. Right? For today, we're going to switch gears a little bit, and we're going to focus in on these two terminologies, strong and weak. We had heard of these words in the earlier lessons, but now we're actually going to do it as a lesson here. When we talk about strong versus weak, it's very, very specific. It's different from you just saying, oh, this orange juice is very strong. Okay? When we talk about things being strong, we were referring to its ability to ionize, and things that are strong are actually completely ionized. Or another way of saying that is you can say it's 100% dissociated. It's 100% broken up. They're no longer holding hands in water. Right? So water is going to be our, we're going to assume water is our solvent, and that's why we can have aqueous. So HCl turns out as our strong acid. So HCl, this chemical, no matter how concentrated it is, no matter if it's 12 molar, really strong stock stuff, or I've diluted it down to 0.01 molar, it's just chemically speaking, HCl is strong. A strong thing that ionizes 100%, this one here will not hit equilibrium. It's wrong for you to put equilibrium there. It's going to separate, the water is going to come in and break off the H+ and the Cl-, and we end up getting H+ and Cl- like that. This is, in some sense here, the simplified form. It's simplified in that it actually just lists the proton. This is what's being released. So you drop this here in water. HCl initially was holding hands. When you actually drop it in water, water is going to separate the H from Cl, and it's going to break off to become H+ and Cl-. But we saw, wait, an H+ is actually just a proton. And this proton here, being so small, so tiny here, it's not stable by itself. What's going to end up happening is the H plus complexes with water. Another example of a Lewis base definition here. The water is going to complex, attack the H plus, and therefore ending up, this one here is an equilibrium, ending up forming our hydrated proton or hydronium. So what's going to happen here is, although in data tables they may actually just leave it as a simplified equation, yeah, HCl ended up releasing off the H plus, we can always change it from the simplified form to the more complex form. In the acid case, it's almost like I'm coming in here and I'm adding water to both sides. So algebra says whatever I do to the left side, I can do to the right side. It keeps things constant. On the left side here, there's no real surprise. It's HCl dropped into a bunch of water. It's still going to be a one-way arrow. It's just the H plus and the water, when they complex, they're going to end up forming our hydronium, leaving you with Cl minus. This is actually what's occurring in solution, although the simplified gives us a slightly simplified picture. Okay, so we have a handful of acids that are strong, H2SO4, HCl, HNO3. They are on our table. We're going to see later on. That's for a strong acid. Similarly, for a strong base here, strong bases, really, it should have just been oxide like this. As a strong base, it has to one-way arrow form hydroxide. That's what ends up happening. Well, where did it get that H from? It has to react with the proton. Someone had to have given it the H plus. This one here is referred to as a strong base. It's the reactant that's referred to as a strong base. It ends up creating hydroxide. Hydroxide, it just happens to be in solution, the characteristic base particle. What's going to happen here is that's the strong base, or remember we cheated a little bit here. We actually threw in those soluble salts again. The soluble salts here, well, what about the sodium? It's just going to be a spectator ion here. It's not actually going to interfere, but it also one-way arrows and forms a space particle. So we had called NaOH any soluble salt that ends up having a hydroxide, we still also capture into the OH minus strong base definition. That's what it takes to be strong. Again, molarity doesn't matter. You can have 6 molar sodium hydroxide, right? It's really, really corrosive, or it could be 0.1 molar here, just chemically speaking, because water has no trouble separating from the sodium from the hydroxide. It's a one-way arrow. For a weak acid or a weak base, this one here is going to only be partially ionized. For a sort of technicality here, anything less than 100 is going to be referred to as partial ionization. Usually what we're talking here is we're usually talking maybe 10% ionizes or 5% ionizes. Really, really little actually ionizes. So if I just make a comparison here, let's take our HCl, which we had done a one-way arrow. This one here was 100%. This one here we call our strong acid. Fine, no problem. There are a handful of other acids. So our acetic acid, our HCN. I can make a whole list. Technically speaking, it's a weak acid because these ones here ionize something less than 100%. We're actually going to use equilibrium constant to actually figure out how much this is going to be, but technically even if it were 99, it could still be referred to as a weak acid. Now just because they're weak acids, however, they're still going to ionize different amounts. So first thing, for weak acids, we're going to use a double-headed arrow because these ones here end up forming equilibrium. They don't fully go 100%. Let me just put some random numbers to this. Let's say the acetic acid ends up going 10% and the HCN ends up going 5%. Yes, overall, they're called weak acid because it's not 100, it's an equilibrium. But you can still have a relatively, acetic acid is still a stronger acid than HCN. So you can make a note here, although all weak acids end in equilibrium. So that means not 100%, not a one-way arrow. It's not like those strong things. Some are stronger. They ionize better than others. So what I'm trying to capture in this table here, yes, they're weak because it's less than 100%. But the acetic acid was still 10%. I just made up that number here. I can still say the acetic acid, albeit weak, is stronger than HCN. So it's a stronger weak acid. This one here is a weaker weak acid. Right. We will see later on, especially when we get to the indicators, most of our organic acids and bases are going to be weak. So let's make a note here. Most organic acids or bases are weak. And it's actually this equilibrium that's actually going to give us some interesting properties, changing colors for indicators, making our buffer solutions for later on. Okay, so we had to use a double-headed arrow. Let's say I take this acetic acid reaction here. So our chiku, chemically speaking, although we had talked about, yes, the H is easily removable, chemically speaking, this reaction doesn't occur 100%. So what's going to happen is we're going to put in equilibrium. We're going to end up releasing up H+, but the equilibrium constant is actually going to be really, really tiny. It's going to be 10 to the negative 5, 10 to the negative 6 or so. So what's happening here is nothing wrong with the mole ratio. For every one of this acetic acid, we are going to get 1 part H+, 1 part acetate. But let me just draw this picture here. Let's say I start off with 1 molar acetic acid. Because we are not 100% and we're only maybe a fraction dissociated, the smidgen that actually dissociates off, I start off with 1 molar, the smidgen that dissociates, we might only end up with, I don't know, 0.1 molar H+, 0.1 molar acetate. Again, it's not that the mole ratio is wrong. The mole ratio says for every 1 part that breaks off, you get an equal part H+, equal part acetate. It's just that the equilibrium is very, very low. Since the Kc, we're going to call it the Ka later on because this is an acid equation. Since Kc is small, it's going to be something way less than 1, 10 to the negative 5 or so. We can say reactants are favored. And this time, more interestingly, because this one here is also aqueous, definitely I'm going to have a lot of it stay on this side. In fact, when we start doing our ice tables to our equilibrium systems again, we're going to imagine that so little actually ionizes over. Practically, this is almost about 1. There's so little that actually breaks off that actually matters. Right? So very important here. We want to use strong and weak here, really, really particularly here. Be careful not to accidentally confuse the word strong, like in this lesson, with concentrated. Right? Usually, when we mean, oh, this orange juice is really strong, we actually mean concentrated or weak with dilute. So, some examples here. If I can have 12 molar HCl, or I can have 0.1 molar HCl. In this case here, just for being the sheer fact of HCl, you are going to be a strong acid. So this one here is a strong acid. It's just that if I'm 12 molar, I can also call you, well, this one here is very concentrated. This one here is very strong stuff. While if I have a 0.1 molar, this one here is very dilute. Right? So molarity and strong and weak have to do with different things. So let's make that conclusion here. Strong and weak refer to the ionization, refer to how easy it is to break up. While if you have molarity, if you have, a high number or a low number here, moles per liter, this one here refers to the amount present. So molarity, this is when we talk about concentration or dilute. That's talking about the amount that's physically present. Okay, so continuing on here, we made that distinction between strong and weak versus molarity as a concentration argument here. It's also very important for us to note when do we use H plus and when do we use H3O plus. Usually, if it's just H plus, it's sort of simplified. On your tables, it's usually simplified here. The H3O plus is actually what's happening. You can very easily rewrite from one to the other. On the acid side, I had already alluded to earlier, it's sort of like adding water to both sides. If I add water to this side and I add water to this side here, it's just going to end up, this one here is so far the simplified equation. The complex equation is going to have HF, and it's going to react with H2O, and it's going to be in equilibrium. The H2O and the H plus together will form hydronium. That's actually what it is when it's complex, and it's going to end up having F minus here. Let's just study in detail sort of, well, what's the difference here? Earlier, I was just saying HF. HF here is an acid. We know it's a weak acid because it's an equilibrium system here. We know as HF's job is to release an H plus in solution. That's the Arrhenius definition. You'll notice in the complex case here, it just gives us a little bit more information. All right, HF here is still an acid. It's still weak because of equilibrium. But who does it actually pass this football to? It doesn't just spontaneously in water just drop off the H plus. It's like it passes the H plus directly to water. The water goes up by an H and a charge, so it's hydronium, and the F goes down by a charge. And that's the difference between a simple and a complex. The simple just shows you, yep, the HF is supposed to release the proton, whereas the complex tells you where the proton ends up going to. In a similar fashion, bases can be described as strong or weak. Strong means one-way arrow. A weak means an equilibrium system on the basis of the extent of dissociation. Another way of saying that is a degree of completion, right? So if it's one direction, right, it's going to be 100%. For example, NaOH dissociates fully. The equilibrium lies really, really far to the right. This one here is a strong base. We're going to get Na plus and hydroxide. Let's imagine trying to do a Kc for this reaction. I know it's not an equilibrium, but if I tried to do it, I would have products divided by reactants. In this case here, NaOH here, one-way arrow, I basically have no reactants left over. It's like almost trying to divide by a really, really tiny number approaching 0, whereas my product is going to be something. So this one here, usually on the table, they'll just say Kc is very large. And because the Kc is very large, we can use this conclusion. The equilibrium lies heavily on the right-hand side here. We actually have more products at equilibrium. All right. However, weak bases, in a similar fashion, weak bases only ionize partially. So those ones there are going to be equilibrium. The equilibrium actually lies very far to the left. So let's take a look at the simple equation. As a base, I am supposed to receive a proton. So simple one will just be, here's my ammonia. I'm willing to pick up an H+. It's weak, so it's going to be in equilibrium, and it's going to end up forming NH4+. Right? That's what it means here. There's actually a little bit of Lewis theory there. I can show you that little bit. We did this on the first class. So I have NH3. NH3 overall is neutral, but it does have a lone pair. If someone comes along with an H+, I can actually coordinate bond. I can actually grab onto the H+. That's the simplified picture. How do you go from the simple to the complex form? Again, there's no real chemistry here. It just sort of gets us to one from the other. For the acid side, it was sort of like pretend to add water on both sides. Pretend to plus water, plus water. For the base, what I want you to do is I want you to pretend to plus hydroxide and plus hydroxide. Right. So let's just try that out. What happens? Well, NH3, when I have H++ hydroxide, that ends up forming water, that ends up forming a complex. We still get our ammonium, which is NH4+, and it therefore leaves you with OH-. And again, basically what that does is it sort of predicts what's the more complex equation, what's actually happening in solution. I know at the end of the day the ammonia actually picks up at a proton, but again, it's unlikely to have free-floating protons just swimming around like that. In fact, what this says now is, well, that proton actually came from water. So NH3 is going to attack the H+, and it's actually the water that actually leaves behind the hydroxide. Oh, good, we got the characteristic base molecule. That's why this still matches up with the definition. This one here, again, is our simple definition. Basically, you can say ammonia accepts a proton. Right? That's its job to be a bronze-telluric base. But who does it steal it from? The complex definition says ammonia steals the H+ from water, and therefore leaving behind the hydroxide. It, as a chemical, didn't need to hold the hydroxide. It was still able to generate hydroxide in solution, right? So because all of these are sort of equilibrium systems here, we're going to refer to Ka for an acid equation. We're going to use Kb for a basic equation here, and based on the size of the Kc, we can actually figure out whether it is products favored or reactants are favored. So just case in point here, all weak acids and weak base associations are reversible, meaning they're all equilibria. So let's take a look at this HF again. HF and water equilibria become H3O plus and F minus. We're going to do this more thoroughly in a later lesson. Let's do Kc for this reaction. Kc is supposed to be products over reactants. That's why I mentioned the better you know equilibrium, it comes back again and again. So these ones here, pretty much everything is aqueous because everything is in solution, except for water. That's going to be a pure liquid. We don't think of water dissolved in itself. So here we have H3O plus and we have F minus divided by HF. Right? So essentially as an equilibrium constant, all I'm going to do is I'm going to redefine, since this is an equation for an acid, we're going to call this one here Ka, and it's going to now be called the acid dissociation constant. The bigger this number, the more the products are favored. It's just that we're going to see later on in our tables, the Ka is actually just going to be some really tiny number. So therefore, again, it's not the mole ratio that's broken. It is going to be one proton transfer. Whatever little bit actually managed to break off, 1 part hydronium, 1 part fluoride, but the bulk of it is actually staying on the HF side. Because it's small, we can actually make that conclusion again. It's actually reactants favored. Even if we're at equilibrium, we end up having way more reactants than products. We can do our Kb expression, so I can actually just flip this around. The F minus, in the complex equation, it steals the proton from water. Also in equilibrium, it forms HF and ends up releasing off hydroxide. Again, I can say, what's the Kc of this? Products or reactants. HF times OH minus divided by F minus. In this case here, because this is a base statement, so I'm going to call this Kb in that case there for the base ionization constant. So more on this in a little more detail in a later lesson. Let's just flip over the page here. So on our data booklet here on table 21, we're actually given a list of these different strengths. Again, remember this part here means the degree of ionization, basically how far along the equilibria actually lie. The strength of the acid, earlier we had just been calling it Ka and Kb, so we'll start there. So strength of acid is reported as Ka and Kb. It's just that because the numbers we're going to look at are actually going to be so tiny, what they're going to do is they're actually going to do instead the power of Ka and the power of Kb. And in general, when you have P in front of anything, the power of, it's going to end up being a logarithmic scale. We're going to see this in a later lesson. Basically, pKa, as an example, is defined as the negative log of Ka. I want the tinier numbers to be the more acidic ones. Because of this negative, if I have a big Ka value, so big Ka means it is a stronger acid, but unfortunately because of this negative here, it's actually going to mean the lower the pKa is actually the stronger acid. So just watch out for that there. Just like on the pH scale, remember, as we get farther and farther down from 7, we're actually getting more and more acidic. That's the same notion here. So the strongest acid is going to be the one that has the most highest Ka, but the lowest pKa. So the lower the value here, the more acidic it gets. Okay. So which acid is stronger? We have acetic acid, and we have this C6H5 acid here. So we'll just go straight to our table. We have the pKa of our acetic acid. This one here is given as 4.76. The pKa of this chemical here is C6H5, the phenol. This one here is given as 9.99. Remember, it was reported as the power of Ka or the power of Kb. In this case here, they're both acids, so Ka. In this case here, remember, the lower the pKa, in fact, it means the bigger the Ka, the stronger the acid is. So we would imagine that between these two here, the acetic acid is actually a stronger acid. If you look at these actual numbers here, starting off with 1 molar, both of these, acetic acid, I can just write it on the side here. Acetic acid is supposed to equilibrium and produce H plus and acetate ions. If given 1 molar, a box full of this acetic acid, you'll notice 0.996 of it stays acetic acid. Even by the time of equilibrium, a lot of it is actually just staying over here. The smidgen that actually goes over is actually 0.004 of this and 0.004. That's already the stronger of the two. Let's take a look at the other one here, our phenol. We have C6H5OH. Again, it's a weak acid here, so it's going to be in equilibrium. It's going to end up giving you H plus and just the remaining C6H5O minus here. And therefore, again, just to play fair, we have equimolar. We have the same molarity of the acid. This one here, in fact, 0.99999. This one here is still on the conjugate acid side. And an even tinier portion actually goes over. We actually only have 0.00001 of both of these ones here. Yes, overall, both of them are weak. Both of them are equilibria. But we can still refer to, so they're weak. We know that because these ones here are equilibria. But we can still refer to the acetic acid as relatively being the stronger one. So let me give you some conclusions here, some comments. So we have, if I want to have a stronger acid, right, an acid's job is to donate a proton. How would I identify which one is a stronger proton? The stronger acid has a bigger Ka and a smaller pKa. And in that situation there, we're going to end up having more ions dissociated because it's stronger. Right? More ions actually end up ionizing over. In a very similar fashion here, we're going to have a stronger base has a bigger Kb. Right? So still in clear constant, it's still Kc, but I'm just renaming it. If I'm talking an acid or a base, in this case here, it has a bigger or larger Kb and actually a smaller value on the ruler. It's actually a lower number. Right? So let's see if we can just practice this here. Just one other note when we deal with this. When you start looking at HI and HBr, you're going to end up realizing, wait a second, both of these are actually strong acids. Both of these actually have a really, really low Ka. Basically, what ends up happening is we have a HI. Because we're strong, we're one-way arrow, we're going to form H plus and I minus in water. Similarly, here with the HBr, it's going to be a one-way arrow, H plus and I minus. This time, we're comparing two things that are strong. This is already sort of maximum strength. They're 100% dissociated. They're no longer holding hands anymore. So here we make this conclusion. In water, since all strong acids are 100% ionized, no longer are they holding hands, we're going to end up with just H plus and just H plus. We can say water has leveled. Water has sort of flattened out. All the strong acids will end up giving you the same amount of H plus, even though the counterbalancing ion, sorry, I meant to say this one here is Br minus. So unlike earlier, sure, we may have equimolar amounts, we may have 1 molar, both of these ones here, because it's a one-way arrow, both of them end up forming 1 molar, H plus. Basically, both of them end up forming H3O plus. So therefore, H3O plus is actually the strongest acid that exists, but the key here is in solution. If I have a pure sample HI and pure sample HBr, I can get them to sort of react by themselves, but especially when I start getting molar, and especially as I start getting solution here, we definitely have been leveled. We're all equal strength because we're pretty much 100% all this hydronium, all this H+. So just to flesh this out a little bit here, we can refer to this as the leveling effect. So in water, basically water levels all the strong acids. All the strong acids, or even throw in those bases here, they're all 100% ionized. Strong acids are essentially solutions of H+, strong bases are solutions of OH-, and therefore the hydronium and therefore the hydroxide are the strongest things that we have in solution. H3O plus here as an acid. H3O plus, surprisingly, H3O plus is actually only a weak acid. It's got an equilibrium to sort of get rid of that proton after it forms a complex. It wants to stay on the side. The H3O plus itself is a weak acid, although it was formed from a strong acid. So the strength of the acid or base here determines its Ka and Kb. It determines at equilibrium how much of each that I have. One other thing that we're going to find here is, especially for amphiprotic species here, the higher the Ka, let's take a chemical here, just for argument's sake here. HCN becomes H plus and Cn minus. Let's say it has a Ka value, right? The Ka describes how easy it is to go in the forward direction. I can also refer to, wait, Cn minus is the base. It's also going to try to go in reverse. It's also going to try to go in Kb. We're going to see this more in a later lesson. The bigger, so if I have a larger Ka for the conjugate acid, in this case here it's HCN, if I have a more of a tendency to go in the forward direction, what does that mean for Kb? The Kb actually should end up as actually a smaller Kb value. Right? Again, we're going to do all this with ice tables and math upcoming. I just wanted to introduce to you not only the difference between strong and weak here, but also some of what the table shows you. So a couple of simple questions here. They're going to specify a particular chemical. They're going to specify a particular, is it an acid or is it a base? See if you can write out the complex equations, right? So on the acid side, it's like adding water to both sides. On the base side, it's like adding hydroxide. Write out the complete equation. If you want to really practice here, see if you can also write the equilibrium expressions. Write out the product over reactant ratio for each of the reactions that you end up with. So I'll leave you to practice some of those there. We'll finish off this lesson here. Sometimes they ask us for sort of some experimental findings. Yeah, I know strong means 100% ionized, 100% broken up. Weak means anything less than 100. Again, for argument's sake here, the 100%, we're usually talking about 5%. That's how low we are, although we could have some that are relatively stronger than others. What are some experimental tests I can use to actually distinguish, oh, this thing is strong or this thing is weak? So a couple key features. For electrical conductivity, remember for conductivity in general, we need to have ions, and we need to make sure that they're mobile. We need to make sure that they can move. So if I have something that's strong, if I have more ions, right, in this case here, it's going to amount to more conduction. So if I have a conductivity meter, which solution actually carries current better, that's actually referring to a stronger solution. So, for example, if I take 1 molar HCl, well, the 1 molar HCl is going to break off completely to become 1 molar H plus 1 molar chloride. So that's going to be 2 molars worth overall. What if I compared it against acetic acid? Acetic acid, unfortunately, is a weak acid. Let's play fair, so it's equimolar, so 1 molar. Again, I'll write that term for you here. Let's assume they are equimolar, so they are the same concentration to begin with. Because the Ka value is so tiny, the amount of H plus and the amount of acetate that I get is a small fraction. We had that number from earlier. It's just small amounts. Because I don't have that many ions, comparing equimolar, I'd imagine the stronger things to be more conductive. Now, it is totally possible. They always like asking the question here, could it have been, let's say, 0.0001 molar HCl against maybe like 20 molar acetic acid? I don't even know if you can get up to that concentration here. Remember, the strength depends on the chemistry. So HCl here is strong. It's going to break up no matter what. But I have a very dilute sample. I'm not going to get a lot of ions. The acetic acid is actually a weak acid. I know it doesn't break off a lot, but if I have a very concentrated sample, it is possible that I could have a weak thing actually conduct better. That's why, to be fair, you have to compare equimolar amounts. Second thing you can test here, just to finish off, we can test rates of reaction. So if I have a stronger acid, whether it's a stronger weak acid or actually a strong acid itself, stronger acids or bases produce ions faster, right? As I get more reactants, they can collide with good energy, good geometry here, so usually a faster rate. So, for example, a characteristic example is you're going to drop a piece of metal into 2 acids here. If the rate happens to be a lot quicker, so let's say magnesium is being eaten away in the acid, the magnesium is taking forever in this acid here. Again, playing fair, if we're equimolar, the faster reaction rate would probably be the stronger. Right? This one here is able to single replace a lot quicker. The reaction occurs faster. Lastly here, we can just stick it on a pH probe here. pH is going to be a meter. Yes, it actually monitors the H plus concentration in solution. We usually put 7 as a dividing line. I want to keep emphasizing this is only at 25 degrees, which we're always going to be pretending. Usually if I have, again, equimolar, strong acids and weak acids here, the strong acids, based on the concentration we look at, strong acids would typically knock us down to the 0 to 2 range, whereas a weak acid, because it's not really good at ionizing, it's going to leave us in the 3 to 5 range or so. Of course, if you have a very concentrated sample weak acid, it can knock us down that way, but just relatively speaking, strong things should be able to ionize more. We get more acid, and remember, the less the pH is, actually the more acidic it is. So strong acids typically are more acidic. It's when pH decreases. Even though we sort of ballpark it with the 0 and 14, we'll come back to this later on. It's just hard to actually get beyond those. You could get really strong acids, high concentration, actually get into the negative pHs, but it's fairly hard to do. More on that later on. Okay, so a couple experimental tests to distinguish between strong versus weak. Strong versus weak have to do with how easy it is to ionize, and that's how we do a test. Right? So practice through those questions and let me know if you have any problems. Thanks, guys.